Howdy. The purpose of this video is to talk about one specific crystal structure, and that is the FCC, or face-centered cubic crystal structure. So face-centered cubic is an example of a close-packed structure, and it's important because it's found in many common metals that we work with. So as an example, aluminum, gold or silver, copper, and certain steels, these would be ferritic steels, all exhibit the FCC type structure. So what is FCC? What does it mean? FCC is the face-centered cubic structure. So how we get this structure is we start with the face-centered cubic Bravais lattice, and we put an atom at each individual lattice point. So the Bravais lattice, the face-centered cubic Bravais lattice, is defined by a cube that has one lattice point on each corner and one lattice point in the center of each of the faces of the cube. There's no lattice point in the very center of this cube. So remember, the definition of a lattice point is that its surroundings are entirely equivalent to every other lattice point. So for example, if I take, here we're going to switch models. If I take one face-centered cubic unit cell, that's the corners have these red atoms, I see a lattice point that's on the center of that face. However, I could offset that unit cell, so now my corners are these white atoms, and now what was a corner before is the atom in the center of the face. So even though this is in the center of the face, this is on that corner, they're entirely equivalent because they're all sitting on lattice points. Okay, so how do we construct a FCC structure? Remember, it's a close-packed structure, and we make close-packed structures by stacking together close-packed planes. Now, this is a little interesting because close-packed planes you're used to seeing six-fold and three-fold rotation symmetry in those planes. And when you just look at a cube to begin with, it's oftentimes hard to see that three-fold rotation symmetry axis, but you'll see it momentarily. So an FCC structure has what's called an ABC stacking sequence. And what this means is that if we start off with one close-packed plane, we stack another plane on top of it, but offset just a little bit. And so A was where we started, B, it's offset a little bit, C, the plane on top of that, is also offset a little bit and not in line with that original plane. And finally, we get back to the original position. So A is in line with A. So ABC. It takes 3 repetitions of stacking planes to get back to that original orientation. So let's see what that looks like. We're going to start off with a single atom, and then put a close-packed plane on top of that. And so you can see that atom through the hole in this plane. So this is our A. B is offset a little bit. So now we're going to put another layer, C, which is also offset. And if you look closely, you can still see that orange atom through the hole of both layers. And so that means that B and C, neither of those are on top of the original A. And then finally, we're going to come in and place another layer on top of that very original layer. So A, B, C, A. And you can continue on. So this gives us our structure, but when we look at it, the planes are falling apart a bit. When you look at it, you immediately start to see the cube. You would see it if I didn't drop it. So this is one face here. This is a square face. So we see those threefold rotation axes of symmetry by looking down the body diagonal from one corner to an opposite corner in that cube. Okay. So that is how we get the ABC type stacking and how we end up with the FCC plane. So we're going to talk about a couple other things. We're going to talk about coordination numbers, and we're going to talk about what some of the planes look like in the FCC structure. So coordination number is how many atoms are surrounding one atom. So to calculate the coordination number, we can start with any particular atom we want. So let's start with this atom, say. So I can see immediately that there are 4 atoms touching it, 1, 2, 3, 4, in that plane. What might be a little harder to see is that there are 4 atoms touching it immediately below. 1, 2, so that's on the right face, on the front face. There would be one on the left face and one on the back face. So that's 4 touching it from below, 4 in plane, and then I would have 4 touching it above. So 4 times 3 equals 12. Coordination number of the FCC lattice is 12. We're going to switch over here and we're going to look at it a little bit differently. Now, any particular atom is going to have 3 atoms touching it from below. So now we're going to consider it by looking at cross-sections of these close-packed planes. Any atom is going to have 3 touching it below and 3 touching it above. And in the plane, if we borrow these two for a second, we can see one atom in the plane has 6 surrounding it. So again, this is just a different way to look at it. But we have 3 below, 3 above, and 6 surrounding. So again, we end up with 12. So 2 different ways to look at the packing, the coordination number, but we're getting the same thing, which is good. Okay, let's try talking about different planes. So some of these planes are really easy to see. So for example, make sure I have this on, the 100 family of planes is essentially what we see when we're cutting the faces of the cube. So there's an atom at each of the corners and 1 atom in the center. So if I were going to calculate relevant lengths, this being the radius of the sphere there, the hypotenuse is 4r. The side here is going to be 2 square root of 2r because it's a 45, 45, 90-degree triangle. And so from these dimensions, you can calculate planar densities of this plane. Let's look at a little different plane. Let's look at a (110) family of planes. So I see all the atoms along this direction are touching each other. However, there's a gap. So if I were to redraw this in 2-dimensional space, it would look something like this. These 3 planes are touching, 3 atoms are touching. And there's a gap here. So ignore this line. So again, we could calculate the length of the plane in this direction is just 4r. The length of the plane in this direction is the same as before, so that's 2 square root of 2r. And so I could count the number of atoms and calculate planar densities. Let's look at one final plane. If I look at a plane like this, this is the 111 family of planes. So if I were to redraw that, I have a triangle, atoms that are touching each other. And so this is, again, our close packed plane. And that's all that I wanted to share.